Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome all to today's session on mastering remote sensing image segmentation with AI, a hands-on workshop with the Segment Anything model. My name is Andrea Manara from the ITU, the International Telecommunication Union, and I'm really happy to introduce a new episode in the GeoAI Discovery series. We launched this series beginning of 2022, and we discussed the GeoAI applications and policies, ethics, and the future of GeoAI for Good. Thematic sessions included climate actions, spatial digital twins, energy, ecology, agriculture, water and food system, health, and many more. Current focus of the series is on geospatial large language model and in the organization of hands-on workshops, which are focused on building up practical skills in applying AI to geospatial data under the leadership of the curator of this series, Professor Maria Brovelli. If you missed some episodes, don't worry. You can watch the recordings of those events on YouTube or in the neural network to which you are connected right now. Without further ado, let me now introduce Rohini and Maria, who will moderate today's event. Rohini is a geospatial expert with 12 years of international experience working with the humanitarian and development sectors. She currently works with Climate and Environment Data Unit UNICEF and previously served with several other UN agencies, and she is a GeoAI enthusiast. Professor Maria is a professor of GIS and Earth Observation at the Politecnico di Milano at the Geoinformatic Engineering course of study, and a member of both the Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her many activities, Maria is Vice President of the Commission of Geospatial Information of ISPRS, member of the Advisory Board of the UN Global Geospatial Information Management Academic Network, and the co-chair of the United Nations Open GIS Initiative. Maria, the floor is yours.
Thank you, Andrea, for this nice presentation. And today we have again another amazing event. And I want, first of all, to introduce our guest. So our guest is Professor Qiusheng Wu. Qiusheng is an associate professor and the director of the graduate studies in the Department of Geography and Sustainability at the University of Tennessee. He also serves as an Amazon visiting academic, and is specialized in geospatial data science and open source software development, with a research focusing on utilizing big geospatial data and cloud computing to study environmental changes, particularly in surface water and wetland inundation dynamics. But he's very famous because he's the creator of several widely used open source Python packages, including GMap or GMap, LeafMap, and Segment Geospatial, which are designed for advanced geospatial analysis and visualization. So If you are curious, you can explore his open source contribution on GitHub at github.com/opengeos. So at this point, I will hand over to Rohini, who is presenting the topic of today.
Thanks, Maria. It's my pleasure to present today's topic. When Meta released the Segment Anything model, or shortly called as SAM, the wider community was quite thrilled. Most of us in geospatial domain couldn't wait to get our hands on it. But initially, you needed a proprietary software where it was released or plugged in. But until Professor Wu came up with the SAMGeo Python package, we didn't have an open source way to use it. So things have changed quite a bit since then. We now have advanced segmentation capabilities to geospatial data. So today's workshop, we will be focusing on, this will be a hands-off workshop, and we will explore how to leverage SAMGeo for accurate and efficient image segmentation of satellite or aerial imagery. We will start with an introduction to both SAM and SAMGeo. And first part would focus more on preparing the data once we get into the hands-on session. And we will have the exercises. And towards the end, we will also have a few post-processing techniques and learn about data visualization. I can confidently say it on behalf of hundreds of our participants who have joined online today. We are really looking forward to this learning episode. Over to you, Professor Wu. We are looking forward to hear it from you.
Thank you, Rohini and Maria, for the introduction. So let me start sharing my screen here. Can you see my screen?
Yes.
Okay. Hello, everyone. Thanks for joining. So for today, I'm going to briefly introduce the SAM model and also the SAMGeo. And you can access the slides by scanning the QR code. Also, you can visit the URL bit.ly/AI for good dash SAMGeo. At the end, we also have the hands-on section. So I probably use 15 minutes just for the brief introduction to show you basically the background of SAM and also the architecture. And then we get into the hands-on section, how you can utilize SAM for doing image segmentation of remote sensing imagery, especially high resolution data. So here is the outline. First, I will briefly introduce the open geospatial solutions. Then we get into SAM and SAMGeo. At the end, I will show you some additional resources if you want to learn more. And then we get into the hands-on. At the end, we should have time for questions and answers. So if you are interested in learning more about my open source packages, you can scan the QR code here, or just go to github.com/opengeos. So these are some of the packages that I have created in last couple of years, including mostly Python packages, but also some data catalog. So right now we have a lot of open access data, but there's no central location. So I try to aggregate data from a variety of data sources. It makes it easy for you to actually looking into the data and also feed the data catalog into your program. If you're doing programming, you might want to retrieve the data. I also have some of the web apps that makes it easy for you to query, and also how to make your data products more accessible to the public using some web apps. So there are a lot of examples in here, and this is everything is open source. So you're welcome to use for whatever purpose, and you're also welcome to contribute to the GitHub. If you have any project that you want to host here, feel free to submit a pull request, and we're happy to host your open source projects on this GitHub organization. So next, let's talk about segment anything model. And the segment anything model was released by Meta in 2023, April 2023. So it's a so-called foundation model. Kind of think about ChatGPT, like for large language model, for text, for images. And segment anything model is primarily for doing computer vision, for segmenting objects from the images. And they released the paper and also all the data, training data set, and also have demo. I don't have time to get into the technical details, but you can see how popular and also how the impact that it has. The paper was published just 2 years, but it already like have 7,000 or 8,000 citations. So this is a very high impact paper, has a lot of downstream applications. And here's kind of the architecture. Very simple. If you are not familiar with machine learning or deep learning, it's the look at the lower left corner here, this image. So basically, you can give the model one image. It's going to give you 3 outputs, and then you can pick up whichever you think is has the highest probability meeting your requirement or your applications, and that's it. So give it one image, you get 3 outputs, and it's going to segment the object from there. And the model itself is pretty big, so it has 632 million parameters for image encoder and also prompt and mask. On the right here shows you kind of general process, but all you need to know is the input and the output. So you can give any images. The nice thing about this is called basically zero shot. Basically, it's a foundation model, so you can classify any images that it has not seen or it has not been trained in the data. So different from our traditional remote sensing classification, you have to have an image. You have to do either unsupervised classification or to supervise, provide some training samples. And those are usually very time consuming to prepare the data. But this one is very powerful because you just give the model something, it will give you something. Of course, it's not going to be perfect, but in most cases, the results are pretty decent. So I will show you some examples later. Here, shows you some demo. And so there are different ways you can classify, basically extract object from imagery. So the first one is called automatic segmentation. So we give an image, the model is going to generate a grid of points. And then, so you can think about it's going to basically group similar pixels into one object based on its surrounding, based on color, based on texture, and it doesn't know what it is. So one thing I want you to keep in mind is the model segment the object, but it doesn't provide the object label. So it has no idea about, for example, here, those are horses or mountains or sky or cloud. It has no idea. It just knows it's one object based on basically mimic our human vision. So there's automatic segmentation mode. Also, you can do foreground and background. So this one basically uses point. So you can click your mouse on the map, and then it can basically extract the object automatically surrounding the points. And again, it's still just based on the texture, the color, and everything. So just like human, we can identify the object from the imagery that we see. So this is called using point coordinates as input prompts. You can provide basically the row and column number, and then you can just use that to pass into the model. So basically, you just need points. You can also have some background. So if there's something that you don't want, you can basically the result is going to be binary, yes or no, foreground object and also background. So if the model provides some result that is not ideal, it has something that you don't want, you add a so-called background points, then you will remove those areas. Also, you can use bounding boxes. So you can provide, for example, the upper left corner and lower right corner coordinates. And then, or you can just do a bounding box. If we extract the object, basically the dominant object within the bounding box, and then we give you the object. So you can think about using the point or the bounding boxes. This is kind of like remote sensing unsupervised classification because you provide the training samples. In this case, it's not really training sample. You just restrict the area, the object within the area, so that the model knows, okay, you're trying to basically extract the object. So in this way, if you are providing the coordinates, providing bounding boxes, you probably already know what kind of label it is. So this is kind of indirect way to assign labels to the object. So using the bounding boxes. There's also another way to do it is using a text prompt. Although this is not officially supported by the SAM model, but you can use other model, for example, grinding Dino to actually convert the text to bounding boxes and then pass the bounding boxes into the SAM model. So basically a two-step process, and then you can still get the object. So there are 3 ways. Basically, you can do the segmentation. And the output will basically 3 outcomes. As you can see here on the right, these are some of the examples. So if you place a marker on the back of a human with a backpack, the model going to guess whether you're going to extract the entire this individual, or you just want the backpack, or you just want a part of the backpack. So it's kind of ambiguous. So the model will give you 3 outcomes, and then you can pick up whichever you want. Sometimes not probably the highest probability. You just need to check the result and then pick up the one you want. You can also automate the process. So this is essentially what it is to give one image, give you 3 outcomes, and then you can pick up whatever you think is most suitable for your applications. And it has no labels, but if you provide a marker, again, most likely you already know the label. So this is kind of an indirect way of getting the object and doing the classification using the same model. Also, they released this SA1B, segment anything 1 billion data set. So it has basically 1 billion, 100 million images, and has 11 million images, 1.1 billion mass. So basically for each images, it's already have those labels, and it trains on a variety of data set coming from different locations around the globe. So you can see kind of distribution here. That means it basically covers all kind of images has been acquired. But keep in mind, there's no really geospatial data, there's no satellite data, there's no really aerial imagery. Most of those are basically high quality photos captured using camera, not using satellite sensors. But this is a foundation model, so it's actually, even though it's not trained on geospatial data, it can still perform image segmentation on geospatial data with some decent result. And the model was trained on like H100 GPUs for 3 or 5 days. So not many of consumers actually like us can train the model ourselves, but we can fine-tune the model. We can use the model to apply to some downstream applications. Again, all the data set is publicly accessible. If you want to fine-tune and train the data yourself, you can also do that as well. So that's the initial SAM model released in April 2023. After 1.5 years, Meta released the second version, Segment Anything Model 2, in August. So it's roughly half years ago. Again, they have the paper, they have the data set, and they also have the demo. So different from the previous one, only doing the segmentation for images. This one can do segmentation on also videos. But you can think of video as a time series of images. So basically, it's still doing images, but the nice thing about this, it has the so-called memory attention. That means you can segment one thing, and then you will carry over, and then you can extract also the object from the subsequent things. And it's very powerful because in remote sensing, we also have a lot of time series images. We have satellite operating and then acquire images all the time. So traditionally, you have to train the model to do segmentation on each individual one. But now we can use the model to just maybe segment the first one, and then you will just propagate to do the segmentation for all of those. We'll look into the hands-on, some of the real-world applications later. But here I'm going to show you some demos in here. It's on the website. It's pretty powerful. So you can do real-time object checking. So give a video. You can pick up, for example, the object you want. Just a couple clicks, and then it will do the segmentation for the entire video. It will keep track of the object, whether the object is moving or it's static. And it's very powerful. So you can see here, especially this, it can have a lot of application in sports. Probably have watched Olympics, right? You can see like when, for example, swimmer is moving, you can keep track of this, and then also keep track of any moving objects. So we can do like some kind of real-time object checking, and it's really powerful and really fast. There are a couple more demos in here. You can see it's not just for high resolution. You can do in biology, in robotics, in pretty much anything that have computer vision involved. If you need to identify something from either images or from video, then SAM2 might be useful for those kind of applications. So that's the introduction to SAM and SAM2. Next, we're going to briefly introduce SAMGeo. So as I mentioned, both SAM and SAM2 were not trained on geospatial data, but we can utilize the model to segment satellite imagery or remote sensing imagery, or particularly high resolution data. And so I created a package and released it, I think 1 month after the SAM was released, so May 2023. And it got quite popular. Everything is open source, so you can check out the GitHub repository. We also published a short paper on the journal Open Source Software. If you find this useful, you're welcome to look into the paper. Next, I'm going to quickly show you some demo. We get into the hands-on applications later, but this just show you how powerful it is. For example, here you can see an array imagery and with all the greenhouses. So you can basically segment the imagery without any additional information. Just give an imagery, it will do the segmentation. And the color here is random, so there's no, the model doesn't know what it is. It's just random color, but you can do some prompting to get the, assign the label to those objects. So similarly, for example, agricultural field boundaries, you can also do the segmentation. easily utilizing some of this. And after that, you can calculate the geometry. For example, if you're looking at some of the mostly circular objects, later after you do the classification or the segmentation, we can have those attributes to do the filtering. You can also get those out of the model. Next one is using the point. So giving an image, for example, I want to extract the buildings. You can just easily place, for example, a couple markers on the map, and then just one click, you will do the segmentation. It's super fast and it's like real time. We get into these examples later, but here just going to show you the flavor, what kind of things you can do to do segmentation without training the model yourself. Just direct apply, you get the result easily. You can also do bounding boxes. So if you're trying to extract, for example, here, trees from an aerial imagery, again, you can just, if you already have some bounding boxes that you get from other deep learning models, you can use this as the input to the SAM model. So keep in mind, the SAM model has three modes: automatic segmentation, or using point coordinates, or using bounding boxes. Or you can use also as text prompt. So text prompt is going to basically extract the bounding boxes and then fit into the SAM model. And this shows you the text prompt segmentation. So you can give an imagery, and then you can say, I want the buildings. Then you extract the buildings. You can extract trees, and then you can change the color. Of course, this is not going to be perfect, okay? So AI is not going to solve all the problem, all the geospatial technical challenges, but you give it save us some time, so you can use some of those initial results. You can fine tune, you can improve your model, or you can improve your result. But it's not going to be perfect. They get all the result, and then you don't need to do any post processing. We're not there yet, but these are some of the interesting applications that has a lot of room for improvement. Similarly, right, I can extract, for example, swimming pool, just type swimming pool, and then you will just extract the swimming pool. Again, behind the scenes, using the grounding Dino to convert the text prompt to extract the bounding boxes, and then use the bounding boxes to fit into the model to get the results. And then you can do some post-processing, for example, regularize the footprints, or you can calculate the geometry, calculate the size, or you can combine it with other data to get more information for each individual object. And next, this is more like using the same tool model that allows you to do segmentation on time series images. So in this case here, I have the Lancet time series data for almost 40 years. And so we can utilize this to do segmentation. So all we need is just 3 points. At the bottom here, shows you the 3 points in the first year. And then you do the segmentation for all the years. The results show you on the right. So you can see how powerful this is, like, without having to change the model for each individual year, because you have the memory, it can propagate the objects, and you can keep track the object, knows, okay, this is the river, and then it's going to keep track the river. And it's super easy to do. Again, we look into these examples later when we do the hands-on exercise. Similarly, if you're doing some water extraction, this also, in this case, just 3 points. So 3 coordinates in the first year of this RC for 40 years, and then you extract all the images for the rest. Super powerful, super easy to use. So all the demo here, there's a link upper right, there's no book, but I'm going to show you how to do it in the hands-on section today. Besides geospatial data, you can also do it for non-geospatial data. So in this case, like a car driving on highway. So if you need to keep track those objects, you just need a couple points, and then we do for the rest. So this is more like real-time object checking. And in this case, you can not only detect the object, you can also distinguish the object. So this is more like instant segmentation. So you can basically, for example, you are keep track of these 2 cars, the red car and also the black car, or the white car and the black car. And you can basically distinguish them, object 1 and 2. So other than compared to traditional segmentation, just, okay, they're all cars, but you don't know like how many cars, for example. If you're trying to keep track in this thing, how many cars in there, and also keep track of when they are moving, then you have a lot of objects. But in this same model 2 here, for example, lower right corner here, at the bottom here, you see like 5 cars, right? So you can put 5 points in the first timestamp, and then you keep track for the rest. That's very, very cool. So last one, for example, not just for high resolution data, you can also do some with like post resolution, but have very high temporal frequency. So this one is the GOES dataset, geostationary operational environmental satellite by NOAA. So you can, for example, the volcanic eruption. So you can basically pinpoint those, and then you can extract the impact area. Of course, it's not going to be perfect, but I mean, these are some of the potential things that we can do. So anything that you're dealing with, if it has a time series component, and if human can see the correlation between these different images, then the SAM model might be able to help you. But if they change very abruptly, there's no really correlation, then the model will struggle. So this is some of the limitations that you might want to be aware. And lastly, I'll show you some additional resources. I do have a YouTube channel that I posted videos frequently. You're welcome to follow the channel for updates. And I'm also posting some of the videos related to SAMGeo Geospatial. If you're interested, you check out the YouTube playlist about doing the segmentation using SAMGeo. I also teach courses at the University of Tennessee here, and programming classes, intro to GIS programming. Everything is open access, so you can check out the course website. Also have the entire semester, so this in-person class, but I'm recording the video and make it available to the public. So you're welcome to check out the video and also the course website if you want to learn how to do some basic GIS programming. And also if you want to develop open source packages, you can check out this one. Geographic software design is the one that I'm teaching this semester. Again, it's still progressing, but you can check out the website and follow through if you want to. So I teach step by step how to build open source packages like SAMGeo, LeafMap, GMap from ground up, from scratch, and some of the practical tools that I'm utilizing every day. So you're welcome to check out the website. So that's all for the introduction. And next, I'm going to get into the hands-on. So you can click the link here. It will take you to the SAMGeo website. So this is the notebook that we're going to go through. Everything is going to be run. You can utilize Google Colab. So what you can do here right now, for those of you who are already familiar with Python, if you want to install this locally, if you have access to GPU, you can do that on a local computer. For users that don't have expenses in installing packages or using Conda, you can right-click here and then just open this one in Google Colab. You do need a Google account, so you need to log into your Google account to run this one. So upper right corner here, you should see this one. There should be a sign-in icon, and then you can click the sign-in. After that, then we can run through the notebook examples. My light's off. Let me turn on the light. Okay. And so first thing, let me give some tips about how to use Google Colab. So upper left corner here, there's a table of contents. So here you can see the table contents, and this is a long notebook, a long document, but you can skip through to go to different sections if you want to. Also on the lower left corner here, there's a folder icon. So this one is where you can check some of the files, because later we're going to generate some outputs. You are going to see the outputs from here. On the right here, right now, you will see this one is connected. So by default, it's going to connect you to the CPU version, but because this one is using the SAMGeo, we need some GPU, so we need to switch to the so-called runtime. Think about this is a virtual computer that hosted on the Google Cloud, and after they close the tab, the computer will be gone, so it's just temporary. So if you have anything important, make sure that you can have a copy. You can copy this one to save to your Google Drive if you want to. And so next, I want to show you, this is important. So make sure that you follow the step here. Otherwise, later you're going to have trouble. So you can, oops. Let me move this one around. So here, okay, I think I'm missing something. 1 second. Let me open again. I'm missing the menu toolbar. Oh, here. Okay. So first you need to change the runtime. So click the menu, the runtime menu, and then click change runtime type. So make sure you do this step. Otherwise, you don't have GPU. It's going to be very slow. In general, if you don't just run it on CPU, it's maybe 5 to 10 times slower. So if using GPU, it only takes 10 seconds, you're going to take probably a minute to get the result. So definitely you need to make sure you change this one time. It's free, but it's not unlimited. I think every month Google Colab give you some quota. So I'm going to basically click the T4 GPU and just click save. After that, up right here, you should see this one right now is connecting. It might take a couple seconds. Depends on how busy is the server. If too many people are using it at the same time, it might be a little bit slow, but just be patient. So you do need the GPU to run this, and it's still connecting. So once it's done, then we can start installing the packages. Hopefully Google is working, connect to the T. For those of you who want to set it up locally, I also provide instruction here, how to create a Conda environment, how to activate it, and how to install the packages using Mamba. All right, now it's connected. So if you click the button, it will show you the system RAM. So basically this will be just the RAM, the memory, and this will be the GPU. So we are connecting to this one and with 15 GB of GPU. So it's a pretty decent one. And we should be able to run all the examples except the last part about the video segmentation. But for other sections, you should be fine. So this is how you can set up the environment. And after that, now we can start installing packages. So just click this button on the left side here, run cell, and then run anyway. So this one is going to install the SAMGeo package and also the grounding Dino. So these two packages, this one is just for doing converting the text prompt to bounding boxes. And we're also going to do the SAMGeo. And this will install all the dependencies that we need. Keep in mind, this one might be slow. It might take you a couple minutes, 3 or 4 minutes sometimes. The only thing is this one, the SAM2. So this model, the recent version right now, switched to using the basically build the package using GPU. So it might take some time to install. If you do that locally using Conda, it's going to be much faster. So just be patient. Click on this one, wait for a couple minutes, then you should be good to go. And after that, I'm going to switch to my local computer, but I will show you some of the things some of the problems that you might run into using Google Colab. So Google Colab is great for people that don't want to set things up on your local computer. But again, it's temporary. So once you close the tab, everything is gone. Next time, if you want to try again, then you need to reinstall the package. So it's not very convenient, but it's good for teaching. So because everyone can have access to this, and then you can open the notebook directly without having to install things on your computer. But it has its limitations. Also, because it has some security issues, not all the packages that works locally will work on Google Colab. So just want you to keep in mind. And there are something that you need to pay attention to. I will point out later what kind of things you need to keep in mind. And I already set it up on my local computer here. So this is kind of similar. This is using the Jupyter Lab interface. But in terms of running the code, the script is very much similar. So I show you step by step how to do that. I have already downloaded this one to my computer. So for example, here, if you're on the SAMGeo website, upper right corner here, you can click the button, and this will allow you to download this one to your local computer. But you do need to set things up, and we don't have time to get into detail how to install locally, but I'm going to open this one just to show you what it looks like if I'm running this one locally. So very much similar on the left side here, I have the table content, and you can run through all the sections because I've already set up the packages, so I don't need to run it. I don't need to install the packages again, but so right now I can just click the button. You will see we're going to import the packages, leaf map, and also SAMGeo. Let me see, it's still running. We are almost there. So just click this one and then be patient. You will notice here it's installing a lot of packages and also a lot of NVIDIA GPU because we're using a GPU machine. So it's updating some of those packages, and that's why it takes a while. But hopefully you should be able to finish this one because in the cloud, it doesn't really matter. It's not downloading images, downloading packages to your computer. It's downloading to the Google Cloud. So the internet speed should be pretty good. And in general, it takes 2 to 4 minutes, depends on how busy is the Google server. But after that, we should be able to continue. And from time to time, if you might want to monitor this one. So later, when we're running the models, pay attention to the one in the middle, the GPU RAM. So if you see the line jumps up and then get close, becomes red color, that means you are kind of close to the limit. Then you might need to restart the section. Basically, you just clear all the GPU, the things in the GPU, and then you start from scratch. But every section is independent. So we can run, for example, on the left side here, I'm going to show you, we have the point prompts, right? We can use the point to do segmentation. We can use the bounding boxes to do segmentation. We can also use text prompt to do segmentation. And the last two sections will be using the same two time series image segmentation and also video segmentation. So we should be able to cover all of those, but the notebook is over here. You can try it out at any time. Just run through the code blocks and then see the result, and then you can make some changes. So it's not super difficult. I try to make things as easy as possible, so you don't need to be. If you run into issues, you can also do it later if you want to. All right, it's still installing. So again, this is very time consuming, and that's why I recommend if you have a GPU, probably the better way is to install locally so that it's one time only. You don't have to install every time. So here, let me quickly show you. I'm going to wait for this one to finish, and then let me start with here. So when you basically use a leaf map, if you run this code block, it's going to load the Google-based map at a certain location. So depends on your area of interest. You can change the latitude, change the longitude, the zoom level, and also the map height. So we're going to use the Google satellite base map, but you can use any other available base map that you have access to. Then we can download a sample image from here. To follow this tutorial, I recommend that you just click the code blocks. Don't make changes because you might be drawing a bounding boxes that's too big. So if your image is too big, you might not have enough GPU to do that. So follow through, just click the buttons. And after the workshop, you can play with it and to figure out what's the size that's suitable for your GPU. So in that way, you're going to minimize the problem you're going to run into. Otherwise, you're going to have all kinds of issues. You'll be like frustrating. But again, this is like generic enough that allows you to do a lot of customization. Okay, finally, so the installation is finished. Now you can just click this button, restart section. Okay, then it should be restarted. The installation log here is very overwhelming. You can just click this button on the left side here and then clear selected output so that it doesn't show up taking too much space. After that, then you should be able to just click the button on the left side, or you can press Control Enter on your keyboard or Shift Enter on your keyboard and then to run the code block. So I'm going to import the libraries. Again, you can pay attention to the, let me zoom out a little bit. Pay attention to the CPU and the GPU on the right. Right now, it should be fine because the GPU, we're not using the GPU yet. Then we can create an interactive map, as I mentioned earlier. Sometimes you pull out this code snippet. This one is annoying because Google Colab, although it supports the Jupyter widget, but you need some special logic to make it work. So right now, this one might pop up, but you can always switch to the original one. After that, we're going to download sample data. So basically, you can draw a rectangle. You can use the tool here, draw a rectangle on the map. But again, I would not recommend right now. Just click this button, use the default rectangle. Then we're going to download the sample data from Google satellite imagery. So basically, it's going to pick those kind of like screenshot and then put them mosaic lamp as a GeoTIFF. Then we can use that to do segmentation. Again, this is only for educational purpose only. I put a note in here. You're not supposed to download that large amount of data from the Google satellite base map. But I utilize this one because I want you to be able to customize to some area. But you can also provide your own data. So in this one here, I show you if you have your own data, you can upload here on the left side. You can upload to Google Colab, and then you can just point these file paths to whatever the data that you have. It should work as well. But again, don't put a large image because this requires a lot of GPU and computation. Also, one thing I want to point out is when you load the imagery, right now, this is the imagery that we have downloaded. And if you zoom in, right now it's not super smooth yet. The image sometimes might not show up. This is basically the problem of Google Colab recently updated to Python 3.11, and some of the things right now are not working perfectly, and this is kind of downside. So it's if it doesn't work, you can always go back to run this one again, or you can restart the kernel if it, for example, right now something is not working well here. If the image is not showing, you can go to restart the section, and then just go to individual one. You need to wait until this one is restarting. So this is something that's right now is a bit annoying. But again, if you want to access to the free GPU, you do need to be patient. It's not going to be instant. And later I'm going to run this one locally. So you need to wait until it's reconnected. If it is working fine, you don't have to reconnect it. But if you are looking at the images, so the only issue is basically the visualizing the local raster dataset, because we downloaded the images to our computer. So you see this one here. Earlier, we already downloaded the images. So it should be here. Right now, it's still connecting. So this one, again, it's free GPU. So that's why it's taking some time. Compared to the CPU, it needs a lot more resources. Okay, we're connected. So let me quickly run through this. And again, don't try to zoom in and zoom out too much. You're going to run into issues. It's going to be buffering all the time. So just run the button, and then later, if you want to export it, you can try it out later. But for now, to save some time and to save like your frustration, just run the buttons, and then we can explore later. So I'm gonna download these images again. It's going to overwrite, and if you click this one, it should show the images. Okay. If you see the buffering, just be patient. So this is the limitation. It's not a problem if you run it locally. So don't try to zoom in and zoom out. We are still investigating the issue. So hopefully it will be resolved in the future. It works fine in the past, but just because the recent Python version and also some dependency issues, so it's not working. Now you can run this one, initialize same class. So if you click this one, so what we're doing here is we're going to use the SAMGeo tool, and we can select the model. So the model have different model, the large, the tiny, also the plus. So different model size. And we're going to use the large one because it gives the best result. And also we're going to set the automatic mode off because we're going to provide the point. So allows you to segmentation. Again, just run this one. It's going to download the model checkpoint. Kind of like you are right now, we're trying to use ChatGPT. So you need to log into your account and then have the model, then you can start utilizing the prompt. After you initialize the model, then you need to set the image. So just run this one. So that means we provide the image to SAM and ask it to do the segmentation. Also on the right here, you should see right now the GPU, like 3.7 gigabyte. That means this model has been loaded into GPU. So the SAMGeo tool here, if the GPU is available, it's going to load into the GPU. So I think the size of this model is roughly 2 gigabyte. And there are also some other overhead. So that's why you see 3.7 gigabyte. In general, you need kind of twice of the size of the model. So the GPU need to be a little bit larger than the model itself. And then once you set the image, you're also going to load the images into GPU. Then you can do the segmentation. So next, this is where we start doing the prompting. So as I mentioned earlier in the introduction, you can provide the point, right? So if you click a point on the map, on the image, you get the row and column number. You're going to pass into the model and then do segmentation. But right now we're using geospatial data. So for example, we're trying to extract some buildings from the imagery. So here, SAMGeo allows you to input coordinates, so not the row and column number of the image. This we are providing longitude and latitude. You can also click on the map. Again, I don't recommend right now, although you can, but because of Google Colab, it's not super smooth. After that, all you need is just SAM predict by points, just calling this function and then provide the list of points. So we are providing, for example, 4 coordinates as a list. And then you can also specify the coordinate system. You can specify the output, and that's it. So this is how easy it is to do segmentation using SAMGeo. So just give an image, provide some coordinates, and then just call the model to do the prediction. That's it. After that, let's inspect the result. So if I'm going to click here, You should see the result. Although it's not very clear, but if you zoom in to this corner here, again, it's spinning. So this one is annoying, but just be patient. If you try to run a code block right now, your notebook probably will hang, and it's not going to work very well. Again, this is only happening happened recently. In the past, it was fine, and so this is the issue that we will run into later. So just wait for this one to finish, then you should be good. From now on, I'm going to switch to my local Jupyter Lab because it's a lot more smooth. And so I'm going to show you quickly. I can run the example one more time here, and you will see how fast it is. So I'm going to run this, download the images. Again, on the left side here, you should also see the results. So I'm going to see here. All right. So this is how the images has been downloaded. And let me uncheck this one. So if you're zooming and zoom out, it should be pretty decent. So it's not going to buffering all the time. It should be faster. Actually, I'm running on a remote desktop, basically connecting to a remote server, but it's here on campus, so it's not. It's much faster, at least compared to Google Colab. Okay, it is still spinning, not so good. But be patient. After that, then I can load the model. So it should be pretty quick because I also have GPU here on my computer. So I'm going to run stick again and show you the result. So basically here, I selected 4 points. Let me move this one up. And clearly you can see it's better. So I have these 4 objects. Basically, I provide 4 points for these 4 objects. And here upper right, I can turn the layer on and off. I can also change the opacity. Right. So just 4 points. Then you can extract the buildings. Right. I don't have to actually manually do the digitization using the traditional process. And it may not be perfect. Also keep in mind the model outputs 3 masks. So 3 options. You can look at the result. You can choose the one that's best. Okay, this one right now is done. And again, avoid zooming and zoom out too much. Otherwise, you're going to be very frustrated. So this is just using the point prompts to do the segmentation. This can be useful if you just want to experiment, but assume that you already have a lot of points. So in this case, I have a GeoJSON file, or it can be a GeoJSON, or it can be shapefile, or any geospatial data format supported by GeoPandas. You can directly use this one to do segmentation, so you can pass all the points all at once. But first, let's visualize this building centroid. I'm going to create the map, and I'm going to load the raster, and I'm also going to place all the markers on the map. So take a look. I have all the red color points. So this is kind of you can do that in the desktop GIS, right? So you load a raster data set and also load the vector data, and assume this is the data that we have, all the centroids. And so this centroid might be through some manual digitization or from some other ways that you get. And now we want to extract the building. So basically your input will be an image and a vector data set. So how can we actually extract the building footprints? Utilize these two. And it's super simple. All you need pretty much just one line of code here. Same, once you load the model, and then you can call the function predict by points. Here, the points coordinates bit, you can directly pass the file path. So it'll be this GeoJSON file path. It actually from the HTTP URL, it doesn't have to be the file locally. So you can actually point into any vector data set. And then you can specify what's the coordinate system of those points. So this one is 4386, WGS 84. Specify the output, and that's it. So I'm going to take a couple seconds to do the segmentation. And now you're done. After that, we can add the result back to the map. So here, because you output this one to the building mask.tif, you should be able to find this one also on the left side here, on the folder here. So this will be the result has been generated. And then now we can inspect it. So we can zoom in to see the buildings, see how cool it is. You don't need to do like train your model. It's going to be able to just use the point. And then the segment anything model is going to basically find the buildings surrounding that point. So right now you can see the color here. The color basically kind of random, but you can probably see the pattern. So the dark color represents larger object. So when we're doing the visualization, it's going to get the value from range, give a color range from smallest value to the largest value. So the value basically based on the size. So you actually can calculate how many pixels within each object. And so all the red color here, those are relatively large object. The blue color, those are usually small object. But you can see it's pretty decent. So it's going to definitely much faster than you try to manually digitize. Or you have to train some dedicated building footprint models in order to be able to extract the buildings. So I can see the building mass here. I can change the opacity. All right. So this is basically just the so-called building mass. It's a raster image. But you might be looking at the result saying that, okay, it's not perfect because there might be some very tiny object. Maybe, I'm not sure you can see some of the things in here. Basically, we need to do some cleanup or do some post-processing. For example, here in this case, we have the building here, the large object, but we also have this tiny one. And this one doesn't really belong to this building, but for some unknown reason, Segment NEC model also extract this one as kind of an object. So we need to clean up. So in that way, we can set us, for example, the minimum size. If the building in general is larger than a certain number of pixels, you can just set a threshold. So the next step is to do the cleanup and also convert it to vector data. What you can do is just call this function region groups, and then use the input from the output above, basically the raster imagery, and then you set a minimum size of 200 pixels. Specify the output is a vector data, and also you can output as an imagery. So let's run this two code block. The result will be an array. So this will be the raster, and this will be the vector. The reason for this is sometimes you might want to do some follow inspection or the data processing. So it will allow you to inspect the raster dataset and the vector. Now we can look at the vector. So this will be the geodata frame. So basically for every building, you can get, for example, the label, individual label, building 1, building 2, building 3. So we give you the instant segmentation. So you know exactly how many buildings in this image. And also the area. So the area will be basically how many pixels. And also the bounding box. Also some geometry attribute, for example, eccentricity, orientation, perimeter, elongation, or something like that. So these are all useful geometry attributes that allow you to do filtering, right? As I mentioned earlier, if you know the size of the building, for example, you're trying to extract large buildings, medium buildings, then you can use this column to do some grouping, or you can use this elongation. So if you know all the building, most likely it's not going to be super long. If for some reason Segment NEC model extract like a wall like very long, then you can use that to remove it. So this certainly save you a lot of time because you don't need to change the model. You can just give whatever imagery and then give couple input prompts, then or just provide vector data, then you do the segmentation and give you the result. So this is using the point segmentation. After that, you can do the regularization. So for building footprint, you want to be something like rectangularized rather than a lot of zigzags. So you can basically simplify the output. What you can call is this one, the regularized function in leaf map, and then you can just look at the result. So now let's compare the result. So the yellow outline here will be the rectangularized building footprint, and the color here beneath, that one will be the raster data set. So you can compare. You can compare the result, right? It's not going to be perfect. This is a little bit oversimplification, and there are some better ways, some other algorithm that allows you to maybe regularize, not so simplify. Okay, so in that way we can improve the outcome. For example, the geometry like this. If you have any open source algorithm like for regularized buildings, I'm happy to know. I'm trying to incorporate a better algorithm so that we can get better result. But for now, at least you can see, compared to just a point right now, we have the bounding boxes. We also have the raster imagery, and pretty much all you need is just 10 seconds. You get the result. Compared to the past, you need to train the model. You need doing some object segmentation or object oriented classification. It's a lot of work, but now with just a notebook, you can customize the input, you can customize the result, and can do all kind of visualization. So anyone can do it. You don't really need a lot of programming skills, just click the buttons, make some changes, then your result, you can see the preliminary results like this easily. Last one I will show you here is so-called interactive segmentation. So this is very useful if you just want to see how the model performs. So you can provide this imagery and then just load the model and then just use this one show map. So I want to show you here how you can actually do the classification. So right, this is the imagery, and this will be basically the panel allows you to do foreground, background, but mostly you just want to use extract object, for example, building here. You just place some marker on the map. So for example, here I want to extract these buildings. If you're on Google Colab, you probably just see a green dot. But here I'm locally, so you can see a marker. So for example, I want to extract these 4 buildings. Then you just click the marker and then just click segment. You see, it's pretty nice. 1 second, you get the segmentation result here. You can turn the result on and off. It's just a random color, so you can see the color here. You can continue to place more markers. For example, here, here, here. Again, you get the buildings outputting right away without having to do anything else. Super fast. So if you sometimes have to do some digitalization, placing a marker, placing a point is going to be so much faster than you trying to draw a rectangle or trying to do all the zigzags. It doesn't have to be, for example, here, it doesn't matter. You can click anywhere you like. It should be able to extract all those buildings. So for example, right, click again. Now I have all the buildings. You can also check this box, regularize. So if you just want the building outlines, I can do this way and then just do the segmentation, regularize. Now you have this also, the yellow color, basically the bounding box of these buildings. After that, you can save the result. Just click one button, save, and then click the file path. For example, here, build mass, maybe 2, and then select. It will save as raster and also vector. So basically you have both of those. I'm going to refresh here. You should see I have the mass 2 vector data. You also have the foreground points. So basically, going to save all the points that you have created. Also, you're going to save you the rectangular. So basically, the rectangularized building footprint and also the raster. So all the images, all the result will be saved automatically. So this really makes image segmentation more accessible. So anyone can do it. Just load the imagery and then use the interface. And then you just click and then you get the result. So this is the first one using point prompts. We have 3 more sections. Due to the time limit, I'm going to go very quickly. Again, the notebook is reproducible, so you can try things out later on your own. But I'm just going to show you some of the interesting applications. So the next one is going to be using box prompts. And so first we want to create a map and then trying to download the imagery. This step is the same as the previous one. So we're downloading the data for the same area, and then we're going to display the imagery. For example, same thing here. Now we have this imagery. So in this time, I'm going to show you same thing. We're going to load the model and we're going to set the imagery. After that, you can display the map. So compared to the previous one, we're using latitude and longitude, a list of points. This time I'm using the bounding box. So you can provide multiple bounding boxes. And so this will be the upper left corner. And this will be the lower right corner. So basically longitude, latitude, longitude, latitude. So you can provide different bounding boxes. After that, you just call the model. So again, the same model, then you can provide the bounding boxes. What's the coordinates of this, the coordinate system of these bounding boxes. And you can specify the output. That's it. After that, let's inspect the result. So in this case, I'm probably just provide the bounding boxes, for example, for these 2 raster images in here. And that's it. So after that, you can save the result if you want to, but you can also, similar to the point that I showed you earlier, if you already have the bounding boxes from other deep learning models, but it's not like very fine boundary, you can provide these bounding boxes. So if you have a vector data set that with like simple bounding boxes, you can provide this one. And then let me show you what it looks like. So assume right now, this is what we're going to do. So we have this theta imagery, and we also have these bounding boxes. But this bounding box is not perfectly the building footprint. It just shows you the approximate location of these buildings. So how can we utilize these 2 data sets to do image segmentation? So you can see here, some of them are pretty good if the building is kind of very rectangular. But if the orientation is not really horizontal or vertical, you're going to have some issues. So with these two inputs, then we can use SAM to do segmentation, because as I showed you earlier, SAM has the bounding box, and also the bounding box doesn't have to be perfect. It doesn't have to be exactly like along the building. As long as it has some approximate location, it's going to be able to extract the building footprint out of that. So let's see how we can do that. Very much similar, just call the predict function and then passing the bounding boxes, coordinates, and that's it. So basically just one line of code. Also, you're going to show you if some coordinates is outside the image boundary. There might be something that's outside. So you're going to basically ignore those. And after that, we have the result. So if you run this one, take a look. So if you zoom in, right now, the kind of the red color, those are the building that we extracted using SAMGeo, basically using the same model too. So take a look. All these are bounding boxes. Again, it's so much better than the bounding boxes, right? So if you zoom in, so now we have all these buildings. As I mentioned, the building mass, we go beyond the bounding boxes. Of course, it's not going to be perfect. You want to see some, for example, this might be shadows, things, or maybe driveway. It's not going to be perfect, but you can inspect. Again, it has three outputs. Right now, we're just using the highest probability one. Also, for this building here, right, because we don't have a bounding box, so the model doesn't know. So because it's going to look for object within the bounding box or surrounding. If it's too far away, it will not. So this is, you need to make sure that your bounding box is going to capture all the objects. So if you have something, for example, missing here, it's not going to be detected. But you can use some automatic segmentation. You can still get the object, and then you can pick up some of those. Or you can use the point prompting. Just place a marker, and then you can get the segmentation. Again, this is super easy to use. As you can see, just a couple clicks and just provide two files, and you can get the segmentation. And lastly, you can extract this one, convert to vector. You can regularize, and then you can show it on the map. So if I go back again here, these are the two different data sets, right? So this will be the regularized, and this will be the muting mask. And that one is the bounding boxes. So compared to the bounding boxes initial one, now we have the better bounding boxes that's not really just horizontal or vertical, right? So you can see the result, the differences here. So we improve basically the bounding boxes, but we also have the raster mass of the buildings. And that's it. So you get all the results just within using those two data there. The next example I'm going to show is using text prompts. So this one is even more interesting. Then we can use some text prompts to just specify what we want. We don't even need to provide spatial data. So under the hood, it's going to convert your text prompt to bounding boxes. So now let's load this area. So in this area, we have a lot of buildings, we have a lot of trees, and I'm going to similarly download a sample images from the base map, and then let's load this imagery. So for example, this is the one that we want to segment. So we want to segment all the trees from this imagery. Again, you can provide your own data if you want to, but I'm just going to use this example. So compared to the SAMGeo tool, this one, we're going to use the length SAM. So language SAM. And it's going to download the model. So this one might take some time. If you're running this for the first time, it's going to download the model and also all the checkpoints from Hugging Face, because basically you need to download all the weights. So this is kind of the pre-trained language model, and it's going to basically based on your imagery, and it's going to extract the bounding boxes from your text prompt. So what we need to do here is to specify what you want. You can specify text prompt. It can be just a word, or it can be a sentence. It could be some phrases, but don't make it too complicated. This is not like ChatGPT, that kind of a powerful large language model. This is a much smaller one. It's designed for doing object detection. So you can try things out. It's not going to be perfect, so but it's interesting. So I'm going to show you something like this. So text prompt, and then all you need to just SAM here. SAM predict, and then this is the image I'm going to predict. This is the text prompt I'm going to use, and the text prompt image segmentation has these two parameters called box threshold and also the text threshold. So the larger the number, the more selective. The smaller the number, the more relaxed, the more loose of your criteria. So the value range from 0 to 1. You can see a more detailed description in here, and let's see what the result looks like. So run the model and then get the result. Now we can show the annotation. So call the same show annotation. and it should show you the result like in here. Take a look. So we have this. So basically, the grounding dynamo extract the bounding boxes, and then it's going to pass the bounding boxes into the same model. So now we have all the trees from this imagery. Again, it's not perfect. You can see some misclassification here. If such objects are very complicated, it's going to struggle. But still, it's going to so much faster than you're trying to manually digitize, or you're trying to use some other ways, because this is also object segmentation. It's going to be much better than you doing pixel-based classification. So similarly, you can also show the image without the bounding box. So you can see this dark green color here. These are all the vegetation mask. And you can also show, for example, just a binary. So yes or no. So if you just want the coverage, then you can turn it one into imagery. Also, the result will be output here. So if you click this, all the result will be saved on the left side. So you can take a look at, for example, the output, the trees, dog teeth. So if you input geospatial data, the output will be geospatial data as well. And lastly, you can convert it one to vector data. So similar to the building footprint, you can do region groups, right? So you have some small objects you don't really want, then you can just remove it, set a minimum size, for example, 100 pixels. Less than that is going to be removed. So you can do the cleanup. And then lastly, let's look at the results. So this will be what it looks like. Just a couple clicks. Now we have the tree coverage for this imagery. Again, it's going to miss some of those, whether it's shadows, smaller trees. It's not going to be perfect, but you can change the parameters. You can play with that and see how it performs. And the last one here is in-text segmentation. So if you don't want to run any call, you just provide the imagery and then just initialize the same model. Now you have this dialog box here, allows you to do the prompting. Similar to the marker, you can click a point, but this one, I can type tree and then just click segment. You see, less than 1 second. So now you do this, you can get the segmentation result. So the same thing like what we did above using the coding. But look at this. So this one is missed. This one is also missed. So that means right now the parameter, basically your criteria might be too high. So by default, we are using 0.25. If you miss too many, for example, a lot of emissions, high emission errors, that means your criteria is too high. You want to basically make it smaller. So I can change it maybe to 0.22 and try it again, see if it works. So segment again, it's much better. So now we have more. But if you change it to a much lower threshold, eventually you're going to extract all the object, then you're going to have a lot of commissions. So this is basically something you need to try it out. There's no a single parameter that works for all cases. You do need to experiment and then find out optimal one for your application. For example, if I made a much higher one, you're going to find just maybe no trees. So right now there's nothing being detected. That means the threshold is just too high. So you need to remove it and then find a combination that works best for your use case. And after that, at the end, you can just save the result. So click save. And similarly, right, trees, 2, select. And you're going to select, you're going to save all the results to your computer. So you're going to have a raster imagery. You're going to have the vector data. So you're going to have all the geometry attributes, the size of the tree, how many pixels. And you can utilize this one to integrate with LiDAR data, for example. Then you can get the tree height, that kind of information. But at least this gives you some potential ideas that how you can utilize same model to do some classification, either on trees, buildings, or something like that. So this is using the text prompt segmentation. The last tool is really where SAM tool shines, is to do video segmentation. And I'm going to show you this one is using time series segmentation. So let me run this one. I'm going to download some sample images from my GitHub. So this one is using the Lancet data time series for almost 40 years. And so inside is basically, after it's downloaded, it's going to unzip. So you can take a look here on the left side. So we have the data from 1984 all the way to 2013. So we have over 30 years of data. So this is basically just a Lancet imagery, clips of certain location. If you have some images, for example, time series for certain location, and then you want to do some image segmentation, for example, extract something out of that, either it's forest or anything, rivers. It needs to be large object that can be detected by SAM. So again, SAM works best for high resolution imagery. It's not going to detect less tiny object if your imagery, if you human cannot see it. So after you download the images, so we have a folder with 30 images, GeoTIFF. Then we can initialize the model. So here, different from the previous one, is using basically not automatic mode, but this one we're using video. So you need to set video to true. Although technically we are not doing video, but video basically is just like a bunch of images put together and then become an image. So this is basically the video segmentation, time series segmentation. So load the model, and after that, you can just specify the input. So the 5 paths will be pointing to this directory, and then just tell the model that, okay, I want to do the segmentation on this video, on these images, on this directory of files, and that's it. So you're going to basically behind the scene, it's going to convert the GeoTIFF to JPEG because the same model doesn't understand geospatial data. All it sees is just a bunch of values, NumPy array, and then it's a time series of numerical values, and you're going to use those to do the segmentation. So here, if you want, you can do some prompting. So we have 40 years of 30 years of images, right? So in order to do segmentation, we need to give some inputs. So this is the first year. You can use a slider here to slide through. It might not work very well on Google Colab, but as you can see right now, this is what it looks like on my local Jupyter lab, right? So you can see I have 1984 all the way to 2013. You can clearly see the river changes, the river dynamics, right? What we want is to do segmentation of these river channels from these images. So in order to do that, traditionally, you need to do the segmentation for each individual one. So you need to have a model for example, 1984, 1985. It's very time consuming. But using SAM, now we don't need that much many points. So all you need, for example, you can select a point here. If you click your mouse on the map, on the imagery, it's going to show you what's the latitude and longitude. The column number and the row and column number, basically the X and Y, also going to show you the value. So in this case, I can just click, for example, select 3 points. You click and just remember the points in here. And after that, you can provide that into the prompts. So in this case, I provide 3 points. And the label can be 0 and 1. So 1 means this is the object I'm going to detect, and they belong to the same object. So but you can do 1, 2, 3. If that image have multiple objects, you want to do some instance segmentation, then you need 1, 2, 3, basically unique numbers. If you just want some semantic segmentation, you just want to treat it as the same river, then you can do like 1, 1, 1. Also, you can tell which frame, right? Because you have a lot of frames, you can say, okay, these markers are for the first frame. For example, in this case, it's 1984. And that's it. So all we need in order to classify these 30 years of images is 3 points in the first year. That's it. So now let's use the show prompt to see what it looks like. So basically these 3 points. So I have 3 markers, green markers, and then tell the model, okay, I want to keep track of this object, and that's it. So after that, you can do the segmentation. So you can either provide in X and Y, so basically column number and row number, or you can also provide in coordinates because we have geospatial data. So you can provide longitude, latitude. If you already know the information, you can also provide the list. So these two are actually the same. The only difference here is that you need to specify the coordinates system if you're not providing X and Y. So if you're providing X and Y, you don't have to. But you're providing coordinates, you need to specify. So these two are basically the same result. And after that, just one line of code, predict the video and see how fast this is. It's done. So the model has segmented all the objects for 30 years within just a second. And after they save the result, so save the result actually takes longer. So the classification segmentation has already been done. So now I run this one and you're going to save the result. So save the segment. If you click your folder here, you see the segmentation result. So if your input is geospatial data, time series images, the output will also be time series images. and then it will be a binary, yes or no, yes or no. So you can actually load this one if you want to. Also, you can do some, you can convert this one to a video. So save video segments, blending, that means you're going to overlay the mask on the original satellite data. So in that way, you can see the video, but you can have access to the original data. So if you provide geospatial data, the output will be geospatial data. So you keep all the geo reference, and it's very powerful. Again, all you need is just like, give me your data and then tell me what do you want. Give me a couple of markers, that's it. I will do that for the rest. And so at the bottom here shows you kind of the output. The kind of a light blue, brown color here shows you the entire river, but we only provided 3 points in here, 3 markers. You extract all the rivers and some other things in here. Of course, it's no profit. You're gonna miss some of these. You can add more markers if you want. So now let's preview the result. Take a look. So this will be the outcome. It's a video, and you can take a look. So with just 3 points, and you get a result. Really cool, right? And it also it has the memory, so you don't have to keep track of all the frames. It just give you all the result. Again, you play the video one more time. So certainly, it has a lot of potential application. Especially if the time series like has some correlation, you can keep track of, for example, airplane, boats, ships, any satellite imagery that we use to do some, for example, monitoring. Then you can use this one to maybe potentially extract all the object without having to worrying about, okay, how they propagate from the first image to the second one, because SAM can do that. So this is application for doing time series segmentation. And the last example here is doing really video segmentation. So this one is non-geospatial. It's like you can get any video and then just tell me what object do you want to extract. So very much similar. You can load the model, and I'm going to download a sample data set. So this is basically a car driving, similar to what I showed you in the instruction slides. Then you can just specify, okay, set the video. And after that, it's just going to load the video into the GPU. And let's take a look. So the images. So similar to the time series, this one has 177 images compared to the previous one with just 30. So this one is a mass dense time series. So in that video, it has 177 frames. Again, if you're trying to keep track of these cards, I can click just your mouse on the image, and it tell you, for example, the X and Y. So all you need to just give a marker for the X and Y for that object you want to keep track, right? So the second one, the white car, and this. So once you get those 2 coordinates, then you can just pass in this to a prompt. So different from the landscape example I showed you earlier, this one is using 1 and 2. That means those are the 2 different objects. This is called instant segmentation, means you have one object, this is a different object, and this is the location. So we can provide multiple points, is a list, and give a label. So it means 1 means this is the object, the foreground object, and in which frame. And after that, that's it. So now we can just show the prompts here, right? These 2 markers, and that's it. So with 177 images, just 2 markers, you will capture the entire object. So all we need to do, just predict the video and see how fast this is. If you have a decent GPU, this should just take a couple seconds. And after that, you should be able to see the video, the output. So if the input is a video, the output will be a video. If the input is geospatial data directly to geospatial images, GeoTIFF, the output will be GeoTIFF with the same geospatial information. And after that, then you can save the video segmented. So it's going to show you something like this. So you're going to have the object, the mask, overlay on top of the video, and then different object going to have different color. So in that way, you can have all the object you want. You can also click your marker on all the cars if you want to keep track of all of this. And not only just the object, because you can also output the data as a bunch of images. So in that way, you can do some post-processing if you want. And lastly, you can preview the result. It's still running because this one has a lot of frames. Again, it's 177, so it's pretty big. Anyway, so this is just a quick run through of some of the applications. There are a lot more potential things you can do, especially with the new AI and also open source large language models. There are a lot more other applications. So follow my YouTube channel. I might post more videos, but this is what I'm going to show you, and you can try it out with your own data, with different locations, see how it works. I'm happy to see other applications that beyond what I'm showing in here. Okay, thank you very much. I know it's very short. I wish I had 3 hours, but the notebook is available, it's reproducible, so you can try it out later with other data. And if you have any questions, you can ask on GitHub. So if you have issues, feel free to go to the SAMGeo website and go to the GitHub. So here you can discussion board, you can ask questions here, or you can open the issue if you find any bugs. Again, this is just side project, so it's not my primary resource. If you know how to develop open source packages, welcome your contribution, and I'm happy to check if you have any additional questions. Thank you very much.
Thank you so much, Kishan. This is incredible. I feel like the future is already here, and I have always been a big fan of your tutorials. I was trying to follow step by step as you were going through, and it's really great to see how easy it is for anyone to follow.
Lastly, just show you the output, right? So this is what.
Oh, there you go.
Yeah, it takes maybe a minute or two, but you can see it's pretty good, and also it's high resolution. So it depends on the input. So you're going to overlay those, and it's pretty cool. It's the result is amazing. So just 2 points, and then a video. That's it.
Oh, fantastic. That's great to see. Some of our participants might have faced some technical issues, but rest assured, we will have the full recording available soon for everyone. Maybe the last 10 minutes, we could take some questions from our participants. I could start from this one from Michael Spicer. Would you say that SAM is a good tool for assisting in building a labeled data set, assuming zero shot is not sufficiently accurate by itself for our purpose? If so, do you think creating a labeled data set guided by SAM would result in any biased data sets?
Yeah, it's certainly useful. I think many people actually, if you look into the original paper, for the same paper, the label that they created, initially use human to do the labels, and then eventually train the model to create the label themselves. And then humans just like evaluate whether it's good or not. So certainly, also for the point prompting that I showed you earlier, you can quickly click a marker and then you can generate the label, and then you can use this one like to fit into other model to fine tune your result. So it's certainly like it's yes, but you also need to be careful. Like don't trust everything the model give you, because sometimes it might be something not what you expect. Just like you're using ChatGPT, sometimes it can hallucinate and then give you some incorrect result. Although it give you a bunch of stuff like talking, like thinking, but sometimes it's nonsense. So you do need to be cautious about result from AI giving you. You need to be critical and then think of, at least ask yourself, does this make sense or not? If not, then you probably need to think twice before utilizing the results.
Okay, thank you, Qiusheng. I have also questions on my side, but before asking my questions, let us see the questions of the attendees. So there is Muhammad Bilal who want to understand which are your system specification. So referring to the ability to run locally all the system, what you need.
So if you run it on Google Colab, right? So here, so this T4 GPU give you 16 gigabyte, and I mean it's sufficient for some application like this. But if you have a large image that has 100 gigabytes, it's not going to be enough. So you need to keep in mind the model itself is almost 2 gigabyte. So you need to at least have 2 gigabyte that can load the model into the GPU, and also you're going to have the imagery. So it depends on how big is the imagery. That imagery also need to be loaded into the GPU to run computation. So you need to many times. So minimum, you need to have a GPU at least maybe 4 to 6 gigabyte to be able to actually run this model. But to run a large one, you need like maybe 8 gigabyte, 12 gigabyte, depends how you the hardware configuration. But you do need a couple $100 to buy those GPU and then install the driver, and after that you should be able to do it. But what I recommend is try things out using the Google Colab first, because 16 gigabyte is pretty decent. Actually, not many laptop has 16 gigabyte GPU. So and try this one out first before you try to invest a lot of GPU. Sometimes the result might not be what you want. But I do have a large, for example, on my computer. So I have 2 GPU that allows me to let me see here, to run large images. But yeah, I would recommend maybe 8 GB GPU, and then at least maybe 32 GB of RAM. So similar configuration to what Google Colab provides. Otherwise, you can run CPU, but like I said, it's going to be 5 to 10 times slower. So if it takes 1 minute to do segmentation using GPU, it's going to take you 5 or 6 minutes to get the result. But from the demo, what I show you is actually pretty fast because I have a better GPU, so that it runs certainly much faster. So for example here,
Thank you.
yeah, you can continue question. Yeah.
I do have one from Natalia Revolo. Could you explain how to contact the base map provider to obtain permission for use based on your experience if you have to write say an environmental analysis paper using this?
And I want to recommend, so anytime your publication you're used for commercial, don't download. I'm just showing you, download the small example is probably fine. But if you're trying to download or automate, it's illegal. So I want to make it upfront. And you can provide your own images. Especially in the US, we have the US net imagery. So that one is 1 meter resolution, very high resolution, but it's only for the US. But if you work outside the US, then you need to find some other data source. Don't try to download from the base map. It's going to violate the term of services. I'm only producing this because I want people to customize and then use the small area for their region of interest. But you cannot derive products out of this base imagery because they have commercial license. They cannot. You cannot do that. You'll be getting into legal troubles if you do that.
Yeah. Yes, true. Please don't do that. We never say that in this workshop. Yes, and I have a very quick question about images. It's my question, and then a question from an attendee. So my question is, but when you were speaking about Landsat, which bands did you use?
Oh, this one right now is only RGB. So, but it doesn't matter. So the model doesn't care about RGB or near infrared, but you give me 3 bands. I do whatever you need.
You have only 3 bands.
Yeah,
it's
only
not
3 bands.
possible
Right
to
now,
use
only
more
provides
than
3
3 bands.
But you can use the red, green, blue, or you can use near infrared, red, green. So the model just see the numbers. It doesn't care like what it is. But as long as the band combination can show you some distinctive patterns that you can distinguish. If human eyes can see something, the model most likely can distinguish that. If human cannot see anything, the model will struggle as well.
Yeah, that is true, but it's on the other side, it's a pity because with the multi-spectral imagery, we have much more. And
then we can fine-tune the model. Yeah, certainly it's not, like I said, it's just the original SAM model is like this, but probably we can fine-tune the model to add more stuff.
It could be that
you need a GPU
sooner or
to
later.
Yeah.
It could be that sooner or later will be improved with more bands. It could be.
Yeah.
It could be.
Hopefully, some like big geospatial companies, they can release some like more same model fine-tune for geospatial. They can deal with like multiple bands. But right now, there are some other foundation models, Clay, and there are a couple also IBM release some of those like for multi-spectral classification.
Sure.
But it's unlike this one, it's like it doesn't care about what data, what sensor, what images. You give me something, I give the result. So this is really like a true foundation model, but we don't have some kind of geospatial foundation model that can be this flexible yet, because it's so complicated. You have different spatial resolution, you have different temporal resolution, and you have SAR data, you have optical data. It's so complicated. Same model is relatively simple because it's just a photo, high resolution photo, and there's not so many like spectral bands and also resolution differences.
Okay, and the question from the floor is by Michael Spicer, who noticed that the shadow are included in some of the segmentation results. And so he's asking if SAM can be used to first identify shadows and then remove those parts from the buildings.
Not directly, but you can do some post-processing. Like I said, it's not going to be perfect. Human can also make mistakes as well. And those are usually based on the pattern. For example, it's very dark color. Sometimes you close and next to the building, it will be basically attached to the building. It might be detected. But you can certainly do that. But you can have a combination of other data. So for example, you have some high resolution LiDAR data, DM. You can actually, if they are two separate objects, you can actually get the, for example, do some zonal statistics with some DM. Then you will know, okay, this one is just round. You can just remove it. And the other way is looking at the geometry that I calculated, showing you earlier. If the shadow or the very tiny, very small, only a couple pixels, you can also remove it. So there are a couple like post-processing things you can do. Another way is you can use some of the deep learning models. They can give you better results in terms of the bounding boxes. So if you already have the bounding boxes for the building, it doesn't include the shadow perfect. But if those deep learning models doesn't give you the exact boundary of the buildings, it only give you a rough bounding box. The same model can still be very useful because it will give you the exact area. So in that way, you remove the shadow using other deep learning models, give you the rough estimation of buildings, and then use the same to fine tune to improve the result. And that's also one potential solution.
Perhaps we could take a couple of more questions before concluding.
Yes, so we have 10 more minutes because I asked for having, if you have time, Q-Sheng,
Yeah, sure.
we can stay for 10 more minutes.
Fantastic. So I have a question here from Andres Baeza Pellets. Could you upload a video teaching how to train the model to be able to detect certain objects that it doesn't detect easily? So Andres has been trying to train it to segment electric lines viewed from Google satellite images using Labeled Studio.
Yeah, this is kind of a very common question, how to do the fine tuning. And you have to think about the purpose using the same model. It's called segment anything. But if you fine tune too much, it become a dedicated deep learning model. So there is no point to use the segmentation. Certainly you can do. There are some people, for example, fine tune the same model to do segmentation on medical images or something else. I think from my experiences, if you're interested in detecting a very specific object, you better maybe just train your own deep learning models. If you focus on some very general applications, SAM does it pretty well because it's like very low effort. You don't need to do much. And I don't have time to do it, but this certainly is on my to-do list, is to fine tune the model, and maybe I'm somewhere here. Again, it's just a side project. I don't have time to do all that, and I'm not really a deep learning expert. I'm just trying to utilize and make it easier for people to use. But there are some tutorials here, like how to do fine tuning, but it's not really geospatial. So I do need to spend some time how to make it really easy. For example, just give you a bunch of folders and then some vector data label, and then just feed into the same model, and then you can detect the object you want. It's not like easy yet, but we are getting there. Just need some time. So if you are an expert, welcome your contribution.
Okay, so another question is a question from Hossein, who is asking if we can segment point clouds, which is also relevant.
Yes. I think there's another package called SAM LiDAR or something like that. This for point cloud. SAMGeo doesn't do that, but you can. I forgot the name. SAM LiDAR GitHub. I remember there's a package. Yeah, called Segment LiDAR. You can find on GitHub. This one is for doing like LiDAR point cloud segmentation, but it's not very active being developed. There's no update after 2 years. But you can try it out. Certainly it's feasible. You can use it to do pretty much anything. So at the end, segmentation model, the same model is basically looking at numbers. So if you can convert the LiDAR point cloud into numbers, then feed that into that, the model might be able to actually figure it out.
Luini, one more question.
Yeah, there's an interesting question from Federico Liporace. Is it possible to use points selected from one image to segment another similar image? For instance, once I have a nice cloud and shadow segmentation for one image, could I use the parameters somehow to segment a similar one into the same classes without providing additional data?
For same one, it's not. It's like right now there's nothing. The model is just like the original same model. But for same two, you can see, right? Just like what I showed you earlier, this is video segmentation. So assume that you already have the segmentation from one image. You have multiple, then you can extract the points all the rectangle or bounding boxes from that thing, and then you just passing to the model. You will do the segmentation for the rest. So it's certainly feasible, but you do need to extract the points. And also for the segmentation, in terms of the point, the cloud, it need to be make sure that they basically it's a sequence. So there's some continuation in those objects. If you're trying to detect cloud, like in this imagery, and then you have another imagery from another year, the cloud are not the same cloud, or unless they look very much similar. Like otherwise, if the object disappear, then you're not going to detect the object, right? So assume, for example, there might be some buildings here, and then there might be some earthquake. The buildings are gone, and even though you're trying to detect the buildings, it's not going to work because it's disappeared. The model cannot see the object, then going to disappear. But there are some cases that, especially in low sports events, I'm going to show you, maybe give you the example here. They seem they're trying to keep track of these two cars, and then it's driving. But at some point, there might be, assume you have a smaller one, and then you might have a big truck in front of the big car. So that means at certain point you lose the car, but you see the big truck. But at some point later, the car drive faster, it comes back again. So the model actually can handle that. Same model can handle that. If you go back to this one here, the input prompts, this is where it's so powerful because you can specify a list of points. So for example, for the frames, right? This is basically just in the first frame. So you can add another point in another frame. So basically here, for example, okay, after frame maybe number 11, the object comes back again. Then you can add another point, it will detect that. So it doesn't have to be continuous. The object doesn't have to be appear in every image. As long as it's like jumping back and forth. If it disappear and then the model lose the object, you add another marker, and in this frame, you will keep track of the rest. But you do need to basically do some like inspection. It's not going to be automatic. Human can see that, okay, this is the same car. The model only has so much memory. So the longer that it disappear, the less likely you're going to be able to see, okay, this is the same object that we are checking. So I haven't played with a lot of like example like this, but it's certainly feasible that you can specify multiple points in different frames.
Okay, other question. Marinus Bon is asking if SAM can be applied for large extents, for example, an entire watershed or even a county. And then I want to add also one point to this question related to the resolution of the objects we want to segment. So if we have a big region with different size of objects of the same class, is it possible to manage it? Because you say there are this threshold, you can change the threshold, but if it is changing patch by patch, what happens?
Yeah, there are two ways. So SAM, although I didn't cover here, SAM also has the so-called automatic segmentation. In that way, it allows you to do batch processing. So, I probably have an example here. If you go to the example and then SAM automated, this one is basically doing unsupervised classification. So you can apply to a large area and then you subdivide into smaller tiles and then you do the segmentation, then you merge the result. It's not going to be perfect because for large images, if you're trying to fit that one all at once into the GPU, you need a large GPU. So depends on how big is your imagery. If you have like 1 gigabyte, couple hundred megabyte, it's going to take some time. So in general, couple megabyte for one tile, couple megabyte, it's fine. But there's a so-called the batch processing. There's a, I forgot, text, maybe, I forgot which one. Text prompt batch, for example. There's a batch mode basically allows you to do, for example, predict batch. That allows you, for example, subdivide the images into smaller tiles, and then you do the text prompt segmentation and then merge the result all together. So it's certainly feasible. And in terms of object, right? Look at this one. This is a pretty decent size images, right? So for the tree coverage, you have some larger one, you have another smaller one. The model can handle that, but again, you need to have a GPU that's enough to be able to handle at least one small tile, and then you just iterate through the tiles to do the segmentation. You can try it out, but in terms of the entire watershed, Think about your image resolution. Think about the object that you want to identify.
Okay,
Look at that
thank
first
you.
before. Yeah.
Yeah, thank you. Thank you. I believe that it's time to call Andrea because we are closing now. So, Andrea, it's your turn now for closing. So, thank you so much, Q Sheng, on
You're
behalf
welcome.
of all of us.
Thank you very much. I really want to thank Q Sheng for this really great webinar. And thank also to Rohini and Maria for moderating this event. Thanks to all the participants for being here. We are sure that you learned new skills in this workshop, as we also surely did. I just want to remind you also that the workshop material is available in the neural network. And of course, you can also watch the recording on the event in YouTube and the neural network. I just want to remind you the next planned event for the GeoAI Discovery. 18th of February, we'll still have Q Sheng, who will hold a second workshop on modeling population dynamics with AI. So always using a foundation model. And then in March, we will have 2 workshops organized by NASA and IBM on Geospatial foundation model. On 19th of March, we will have a Earth observation foundation model with Prithvi, EO 2.0 and TerraTorch. And 26th of March, we'll have foundation models for weather and climate. So stay tuned for these exciting developments in GeoAI and Geospatial foundation models. And again, I thank you, all of you, for your participation. And with this, let me give back the floor to Anna. Thank you very much.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.